Okay, this is the online lecture for Geology 1403, Physical Geology, and I am Dr. Kevin Barrett. Today we're going to be talking about metamorphic rocks. Now this is the part of the rock cycle. We've gone through igneous rocks, we've gone through sedimentary rocks, and now we're on metamorphic rocks. Basically, a metamorphic rock is any of the other rock types that have been changed through extreme heat and pressure, basically cooked within the earth, and the rocks change. So sedimentary rocks become metamorphic rocks, igneous rocks become metamorphic rocks, and metamorphic rocks can even be changed back into another form of metamorphic rock. So it's all part of the rock cycle. And it's kind of like baking a cake. You have the ingredients and you put them in a pan, you stick them in the oven, and then those ingredients are the same, but they're just cooked and they become like a cake. Well, coal, for example, bituminous coal, if it's undergone extreme heat and pressure, well, it can become anthracite, which is another form of coal, which has a higher carbon content. Shale, a sedimentary rock, well, if it undergoes extreme heat and pressure, it can become slate, which is a metamorphic rock. If it undergoes even more heat and pressure, it can become a higher grade metamorphic rock that's called a phyllite. Shale and basalt, if both of those are exposed to extreme heat and pressure, well, they can become a type of metamorphic rock called a schist. Granite, heat and pressure turns it into a gneiss. So different types of metamorphic rocks are formed then from these different parent rocks, and we call these protoliths. Talc is a protolith for something called soapstone, a metamorphic rock. Sandstone will become quartzite. So sandstone then is the protolith. Number 1, giraffe. Limestone is a protolith, undergoes extreme heat and pressure, and it becomes a marble. It's interesting that these different rocks, the sedimentary rocks and the metamorphic rocks, will actually display some of the same characteristics. One of the tests that we use to determine if something's a limestone, a sedimentary rock, is the fizz test, the acid test, the hydrochloric acid. If you drop a little drop of hydrochloric acid on the limestone, it's going to fizz. The same thing with marble. Drop a little drop of the hydrochloric acid on the marble, and it will also fizz. Basalt and gabbro, those are igneous rocks. They can undergo extreme heat and pressure, and they can become a metamorphic rock called a greenstone. So metamorphism then is when you expose the rocks to high enough temperature and pressure. It's enough to change the rocks, but it's not high enough temperature to melt the rocks. That's very important. The temperature is not high enough to melt the rocks. If the rocks melt, they're going to become a magma, which will then end up being an igneous rock. The changes to the rock occur when they're solid, so in the solid state. Old minerals, which are unstable under these new pressure and temperature conditions, recrystallize into new minerals, and new rocks are then called metamorphic rocks. Metamorphism occurs at depth, meaning deep beneath the surface of the earth, where there's high enough pressure and temperatures to really cook these things. You cannot see this metamorphic process underway unless those rocks are uplifted and they're exposed at the surface after they've gone through this process of metamorphism. So some of the controlling factors then are going to be the parent rock composition. This is also called the protolith. So again, if you think about the rock that you're talking about, for example, the limestone, the sedimentary rock, that's the protolith of the metamorphic rock, which is going to be the marble. So the parent rock composition is going to control what type of metamorphic rocks you have. Also, the amount of temperature and pressure that's present during the metamorphism. Again, a higher temperature and pressure is going to lead to a higher grade of metamorphism. Tectonic forces. Most of the time we're talking about this occurring where we have extreme tectonic forces which can force the rocks deep beneath the surface of the earth where they can undergo this extreme heat and pressure. Fluids, the amount of fluids that would be available, particularly water. Water that precipitates from rocks can enhance the metamorphic process, the cooking process, and the amount of time. For the metamorphic process to occur, we're talking about thousands and millions of years. Again, the geologic time scale. So the parent rock composition then No new material is added to the rock during the metamorphism. It's the same material that we start with the original rock. There's nothing new that's going into this metamorphic rock. So the metamorphic rock is going to have that similar composition to the parent rock. So again, here's limestone, the protolith, which becomes marble. As you can see by the chemical formula, it's the same chemical formula, the same makeup for both of these rocks. If the parent material contains only one mineral, then the resulting metamorphic rock will only have one mineral. But the mineral is going to be recrystallized, and so the texture is going to change. So it's going to have a different texture from its protolith. Here's an example of limestone. We have limestone under a microscope, and you can see that if you look at the limestone under the microscope, well, you can see these little shell fragments that are within the limestone. And remember that limestone, the depositional environment is deep marine, so these are seashells, old sea life that's died and it's fallen to the bottom of the ocean, and it undergoes lithification and it becomes a sedimentary rock. Well, after that limestone undergoes metamorphism, the texture is going to change. So if you look at marble under a microscope, you can see these interconnecting grains. It's much more tightly compacted and cemented together as that texture is changed. If the parent material contains many minerals, then the old minerals are going to recombine to form new minerals. So clay, quartz, mica, and volcanic fragments in a sandstone, they're going to combine to form some new metamorphic minerals. An example of this is garnet. Now, garnet is something which will grow during metamorphism. Here is a garnet inclusion, and you can see this dark spot here and here and here. Those are garnets, which are growing during the process of metamorphism. And this is a garnet schist. So this is a type of metamorphic rock that has these darker colored inclusions, and those are the garnets that are growing during the metamorphic process. Temperature. Heat from the Earth's deep interior is what we're talking about. Remember that the further you go down into the Earth, the hotter it gets. And all minerals are going to be stable over a certain temperature range, but once they pass that temperature range, they're going to become unstable and start to change. However, if we hit a certain temperature, that high temperature can cause melting. And if the rock melts, it's not going to be a metamorphic rock. It's going to be an igneous rock. So heat is essential, but not too much heat. So we think about mixing flour, yeast, water, and salt, and then, well, nothing happens until they have the heat source, and then they make bread. Of course, you don't want to put too much heat to the bread, or it's going to catch fire and burn, or you'll have nasty bread. That's kind of what we're talking about with the metamorphic rocks. You don't want to have too much heat, or else it's going to melt and become an igneous rock. Number 2, blue. Okay, pressure during metamorphism. Pressure in the earth acts the same in all directions. So if we send something down into the earth, the pressure is going to be the same on all directions of whatever we're sending down. So if it's a rock and we're sending it deep within the earth, the pressure is going to be the same in all directions. So pressure is then proportional to the depth in the earth. And we can say that it increases at about 1 kilobar per 3.3 kilometers. Now, I don't expect you to remember these numbers specifically. Just know that the pressure is proportional to depth within the earth. The deeper you go, the higher the pressure. So, kind of an analogy that we can make is what happens in deep water. So we know that as we go below the surface of the ocean, the deeper that we get, the more pressure there is. And the pressure is being exerted in all directions. So in this case, we have a diver, and he's down here deep within the waters, and he's in one of those deep diving suits. And you can see the pressure is being exerted on the diver in all directions, not just from the top, but also from the sides and from the bottom. If it was just being exerted from the top, then the diver would be crushed. But luckily, again, it's being exerted in all directions. So the pressure increases with depth, but that means that the volume is going to decrease with depth. So if we send a cube, we start with it up here closer to the surface of the ocean, we send it down deep within the ocean, the pressure is going to be greater, and so that cube will become smaller. So the deeper you go, the pressure is going to increase. Here's an example of that happening in the ocean. If we send a styrofoam cup, here's a styrofoam cup as it would appear at the surface. We're used to seeing these. The deeper you send in the ocean, the more it's going to be crushed. Here's an example of a styrofoam cup that was sent down in the Antarctic Sea on January 10th of 1988, and you can see how much it's been crushed. Another styrofoam cup was sent a little bit deeper, and you can see it's crushed even more. So the volume is going to decrease the deeper you go in depth. And then as you come up, the pressure is going to decrease, and then that pressure is going to kind of let go, and the objects are going to be able to expand. The volume will increase as you come up. So again, this is the deep water example. The consequence is the cube is squeezed into a smaller cube. If we look at that and compare it to a metamorphic rock, the grains in the metamorphic rock are going to pack together and become more dense. So high pressure minerals then are more compact and dense than their protoliths. Okay, tectonic forces, this is what's driving this stuff. I mean, it's driving the metamorphic process, and that's driven by the plate motion. This leads to forces that are not equal in all directions, or differential stress at sometimes. Now, if we're sending the rock straight down deep within the earth, we can have pressure in all directions. But with tectonic forces, the pressure can actually be in two directions. An example of this, well, compressive stress. It's like your hands are squeezing together, and this will cause a flattening at 90 degrees to the stress. So in picture A, you can see that we have the compressive stress, so we're pushing down with this hand, we're pushing up with this hand, and we have a dough ball in between. So the dough ball is going to flatten out. Now, if you look at kind of a simpler picture of this, here's we start with kind of a square shape, and then if we put pressure in two directions, it's going to flatten out that square shape. Yeah, this is going to happen to some of the metamorphic rocks. We can also have a shearing stress, which is like the hands rubbing together. In this case, we have the hands which are pushing down, and this hand's pushing up, but this hand on top is pushing to the right, and the hand on bottom is pulling to the left. And so then we get a stress that's going to end up causing the shearing. So it's a flattening and then kind of a moving and a shearing process for this shape. If we look at a metamorphic rock where this occurs, you can see this flattening of the pebbles, and this is occurring because we have pressure that's pushing down from the top and pressure that's pushing up from the bottom, and it compacts these pebbles in this metamorphic rock. Fluids are important because fluids, you could think of the fluids as enhancing the cooking process. And water is going to be the most important. And we're talking about hot water, and when it's really hot, water makes steam, water vapor. So the water vapor becomes the most important. Heat will cause unstable minerals to start to release water. So the process of adding heat to the rock is going to allow the minerals to start to release this water, and so the water vapor will become available. Water reacts with surrounding rocks, and then it transports dissolved material and ions. Time, the amount of time, it's going to be millions of years. Again, we're talking about that geologic time scale. This is not something that's going to happen over just a few years. It's going to take a long time to cook these rocks. And the longer the time that the rocks cook, it's going to allow the minerals to grow larger. Much like the igneous rocks. Igneous rocks that are cooling below the surface of the earth are cooling very slowly, and so the minerals grow larger. With the metamorphism, the longer the time it takes, the better chance the minerals have to grow bigger. And so you end up with coarser grained rocks the longer that they cook. So the basic classifications then on metamorphic rocks are based on rock texture. We can have the foliated metamorphic rocks, which tend to be layered. And an example of this is kind of the slaty type of foliation. It would look something like this, where you have these layers of rocks. And in slate, they used to make blackboards out of slate, and it's fairly flat when you break these things apart, thin and flat layers that will break apart from the slate. Non-foliated rocks are going to be non-layered. An example of this would be the marble. And again, this is what limestone turns into once it undergoes this process of metamorphism. So foliated rocks are going to be the layered metamorphic rocks. And so here's an example of foliation. And this results from the differential stress. So again, this is the type of stress that's not equal in all directions. In this case, this is stress that's coming from two directions. In this diagram, it would be from the top and from the bottom, squeezing this rock together. So again, this type of stress that it's undergoing. So the appearance of this under a microscope, to compare the two, A is showing an example of a non-foliated rock. Again, pretty much these crystals are they're different sizes and different shapes, but they're not showing any kind of a layering. If we look at the foliated rock on diagram B, you can see that there's a definite layering that occurs as these minerals are squeezed together. Now, metamorphic grade. As we said, the higher the temperature and the higher the pressure, the higher the grade of metamorphism. This means that under a very low temperature and lower pressures, you're going to end up with something like a shale, and then getting into the slate. So a slate is going to be a lower grade of metamorphic rock. As you start to increase the temperature and increase the pressure, well, then you end up with a phyllite, and then eventually into a schist, and then eventually a very high grade of metamorphism would be a metamorphic rock called a gneiss. If you get into the point where the rock would be melting, or just almost to the melting point, you can get to a top of metamorphic rock that's called a migmatite. And a migmatite, again, it gets almost to the point of melting, but just not quite. And if you notice, we have different index minerals. So the different grades of metamorphism will determine the types of minerals that we see within these metamorphic rocks. Clays would be something that you see in a very low grade of metamorphism. And basically at that point, the rocks are not going to be altered. They're going to remain more or less the same. It's only until you get this extreme low grade of metamorphism where the rocks will actually start to change into the metamorphic rock of slate. And then you start to see different minerals, chlorite, muscovite, and biotites. You get up into the intermediate grades, and you'll start to see the garnets, the starlites, and the kyanites. But what's common to all the metamorphic rocks is throughout the grades of metamorphism is they're going to have the feldspars and the quartz. So the metamorphic grade is determined by the amount of pressure and the amount of heat that's applied to the rocks. Number 3, the shape is an oval. Okay, types of metamorphism. Contact metamorphism. This is going to occur adjacent to magma bodies intruding cooler country rock. And so we think of this as this magma is trying to reach the surface of the earth, and so it's a big blob of magma, and as it's coming up, it's going to exert some force. And remember, it's magma, so it's hot, and so it's going to be exerting the heat and the pressure. And so this country rock that would be surrounding this magma blob is going to be cooked. And so this is the reason we consider it contact, because it's almost in contact with this magma blob. And so here is an example of a magma blob that's coming up, and here's the magma, and then around the magma, remember we see this brick-like pattern that usually indicates a limestone. Well, this limestone is being cooked, and so around this blob of magma we have this marble that's being formed during the process of metamorphism. And you can see that the water is enhancing this as the water is coming up, and it's reacting with the rocks to enhance the metamorphic process. Now, this type of metamorphism is going to produce non-foliated metamorphic rocks. The pressure is going to be the same in all directions. This happens within a narrow zone of contact, usually less than 1 to about 1,000 meters wide, and this is known as aureole. This is going to form fine-grained hornfels or coarse-grained marble rocks. So again, the marble is what we're seeing. It's the cooking of the limestone. Regional metamorphism occurs over a wide region and mostly in deformed mountain ranges. So if we look at this, we can see that here's a mountain range, and you have a rising magma that's coming up, and as this magma is coming up, the tectonic forces are pushing from two different directions. You can see that you have a force that's pushing this direction and a force that's pushing this direction, and it's basically squeezing everything together. So you have the magma, and that's some heat that's going on. Most of the stuff that's down here is deep beneath the surface, so there's extreme pressure, and again, that pressure is coming from the sides as well as heat as you're deep within the surface of the earth. And so this is when you're going to see this regional type of metamorphism going on. This is going to produce foliated metamorphic rocks, and this is going to happen at high pressure and over a range of temperatures, because actually the temperature is going to be cooler the closer you are to the surface and much hotter the deeper you go below the surface of the earth. So the increases in pressure and temperature forms rocks of higher metamorphic grade. So the deeper you are, the higher the metamorphic grade of the rock. You notice that up here close to the surface we have slate that's being formed, and the slate is that very low grade metamorphic rock, whereas the gneiss and the migmatites are up there on that high grade of the scale. So plate tectonics then are very important in metamorphism. So regional metamorphism is associated with convergent plate boundaries. This is when the plates are coming together. So here's an example, and this is a convergent plate boundary, and this is where oceanic crust is being forced beneath the continental crust. The continental crust is thicker, but the oceanic crust is thinner and a little more dense, and so it's being forced beneath this continental crust. We actually have these isotherms. These are these kind of pink dashed lines, and that's showing a constant temperature. And what this is actually indicating is that at certain points, especially where this rock is diving down deeper, the temperature is not as high. So you'll notice that up here on this continental crust, the temperature is 300 degrees Celsius. If we come straight over, that temperature is actually going to be cooler there. If we look here, the temperature is 600 degrees Celsius on the continental crust. If we come straight over into the oceanic crust, it's 300 degrees Celsius. That's still very hot, but it's much hotter on the continental crust. So as this is being subducted, it has to go fairly deep within the earth before it reaches a very high temperature range. Notice that we actually get down into the mantle, and we're talking about temperatures of 1100 degrees Celsius. So it's going to be much hotter here. So this rock is being forced down basically on this side where it's hotter over here, which is closer to the continental crust. So the pressure is going to increase with depth as it goes down, and the temperature is going to vary laterally. So it's going to vary depending on what you're looking at with this plate convergent boundary. So you have different pressure and temperature conditions, and they're going to yield different degrees of metamorphism. So the temperature is cooler in the downgoing subducted plate. Again, in the dashed purple line or pinkish line is going to be an isotherm, and isotherms again are lines of equal pressure. So we have other types of metamorphism which become a little less common. Something that can occur is this partial melting that occurs during metamorphism. We said that if the rock melts, it can't be a metamorphic rock, but it can get almost to that point of melting, and maybe a little bit of melting occurs. An example of this is a migmatite. And a migmatite is kind of this in-between rock. It has kind of the features of an igneous rock and also kind of this metamorphic texture to it. Another type of less common metamorphism is something called shock metamorphism, and this is going to occur during large impact events. Well, what is an impact event? Well, it's this. A giant meteor hits the Earth, and it's going to have extreme pressure and extreme energy that's going to be released during that impact, and that's going to end up forming some metamorphic rocks. And these metamorphic rocks are not going to take millions of years. You're talking about seconds to form because of this extremely high pressure that's exerted over a very short period of time. So it forms what we call shocked rocks around impact craters. So if we go to one of these large impact craters, we may find some of these shocked rocks, but again, it's very uncommon because we don't see this a lot. Here's a closer look at a migmatite, and we often find these near these igneous intrusions. So here's a granite. So that's an intrusive igneous rock. And then you have the migmatite, which is right next to the granite. You can see that this at one time, again, was a magma. And so this was literally cooking this rock that's sitting right next to it. And some of that is partially melting, but not quite all of it. And so it's going to exhibit this texture that's going to be almost intrusive igneous like. It's going to almost look like granite in texture. Number 4, baseball fans. Metamorphic facies. We can have a group of metamorphic rocks, and we can characterize those rocks by particular minerals that are formed under the same broad temperature and pressure conditions. So basically, this is a way to kind of map out where we see these different types of metamorphic rocks, and then we can look at that and determine what kind of pressure and temperature that they underwent. And so they're named after the most characteristic rock or mineral in a certain area. So we start with this, and this is showing the different types. And so we have the pressure that's over here, and the pressure is going to be directly related to the depth. So that's the reason we have those on both sides of this scale. And at the bottom we have the temperature. So it's cooler over here and hotter over here. So we have the highest pressure over here, up here rather, and the lowest pressure down here. So something that would undergo an extremely high pressure under a very low temperature would be a type of facies we call a blue schist. If we get up here to extremely high temperatures, then you're going to get mostly this type of facies called a granulite, and then we can kind of go in between. And so what we can do is kind of map this out. So we notice that we had the blue schist, and the blue schist is it's not going to be very hot, but it's going to be undergoing extreme pressures. And you notice where that's located. That's located right at this convergent plate boundary, and so it's being forced into the earth, so that's undergoing extreme pressure, but it's not really hot. If we get over here to some of these different facies, we'll see that the GR is the granulite, and the granulite is going to be undergoing extreme temperature as well as pressure in some parts of the granulite. You may have noticed on that previous diagram that the granulite kind of goes across the scale as pressure because the heat becomes the most important, and so this is undergoing extreme heat. And so we can map these things out then as far as where they're forming, and then we can tell what kind of pressure and temperature that they underwent as they were forming. So that's it, and this is the first online lecture for metamorphic rocks. And just as a reminder, some of those things that were popping up, the 1, 2, the 3, and the 4, that's what's going to be on the quiz. So that's just kind of to make sure that you've watched this little short video. And so we'll be taking a quiz over those things that you saw in this lecture. Until the next time, I'll see you in class.